Hello everybody, and welcome to our video on the chain rule. So the chain rule is our derivative rule for dealing with composite functions. So composite functions, we've talked a lot about here and there throughout the course. That's when you have one function that is replacing the input of another function. So to sort of motivate this idea a little bit, we can think of something very simple like a car. Right, so there is some function that governs the input x, so this would be, say, your foot, and your brain decides, hey, how fast do I want to push the pedal down, and how far down do I want to push it? So this is the pedal motion. And then there's another function that governs your car's computer that says, hey, based on how far we sense the pedal being pushed, right? How much gas, or if you're driving an electric vehicle, how much electricity is going to be used to create torque to the wheels and accelerate the car. So in this case, the input for this function g, the car's brain, is the output from you deciding how fast and far to push down the pedal, right? So this is exactly what we mean by a composite function. This input is being evaluated first and fed into a new machine to be used as the input for that. So when we deal with these types of functions and their derivatives, things can become a little bit more complicated. So we're going to take a look at the chain rule here. The chain rule says that if f and g are both differentiable, and cap f equal to the composite of f and g is the composite function defined by cap f of x equals f of g of x. Then cap f is differentiable, and df dx equals df dg times dg dx. So this is why I discussed earlier that prime notation becomes a little bit of a problem once we deal with the chain rule. Notice that this chain rule says that this derivative of the outer function is taken while treating g as the variable, and then you're multiplying it by the derivative of whatever that g is, taking x as the variable. So in prime notation, the closest thing we're able to write, the only way we can write this, we should say, is f of g of x all prime equals f prime of g of x times g prime of x. But there's some issue here because this f prime would typically make us think to take this derivative with respect to x. But that's not the case. We need to take this derivative with respect to whatever that variable g is. So I find that typically students make a lot of mistakes when using prime notation for the chain rule, and it causes a lot of confusion. So I'm only going to do chain rule problems using the Leibniz notation. If you see examples outside and you decide you want to use prime notation, I'm okay with that, but I would warn students to be wary that it makes you prone to some more mistakes. Now, Leibniz notation seems very intuitive here because when we look at this df dg times dg dx, and we say, oh, this is equal to df dx, it kind of, so it looks like that you're just canceling dg over dg. Now this isn't quite right. Sort of. It's sort of right. But there's a little bit of a problem, which is that we can't divide by 0, and there is no guarantee that dg, or I should say delta g, the difference between the input and output of g, there's no guarantee that that isn't 0, which would obviously cause us some problems. So it's not quite right to say that you can just cancel like this, even though it works that way, and we'll kind of treat it that way as we're doing problems. But proving it is a little more difficult. So this is probably one of the toughest proofs in the class, But nonetheless, we're going to go through and do the best we can to understand it. And then we'll do a bunch of problems, and you'll find that applying this is much easier than proving it, and shouldn't be too much of a problem. So first we need a little bit of setup notation-wise. So recall that if y equals f of x, when x changes from a to a plus delta x, then delta y is the difference between f of a plus delta x minus f of a. So we're saying is when we go from this input to this input, the output goes, the difference in the outputs is this minus this. That's all. So by definition, this means that the limit as delta x goes to 0 of delta y over delta x is f prime of a. It's the derivative here at a. So if we denote epsilon equals delta y over delta x minus f prime of a, we should see, it should be pretty clear that epsilon will approach 0 as delta x goes to 0. So when delta x goes to 0, this approaches f prime of a. That's what it means to be a limit, right? So if that's approaching f prime of a, then this will approach 0 because it'll be like subtracting f prime of a minus f prime of a. Okay, so what does this imply? This implies that, also further implies, so we're noticing this, and then we're also noticing that if I subtract f prime of a, or I should say add it to both sides, and multiply delta x across, I get that delta y equals f prime of a times delta x plus epsilon times delta x. So this is just some preliminary setup to consider for now, and we'll move on to the actual main part of the proof. Okay, so here we go. Suppose that u equal to g of x is differentiable at a, and y equal to f of u is differentiable at b. And b is the output of g of a, right? Because we're thinking of this as f of g of x, right? And b, the input into f, is really the output of the function g. So then, delta u, by this work up here, delta u, is g prime of a delta x plus epsilon 1 delta x. So all we're doing is just plugging that into here. And we're going to deal with a few of these expressions. So we're just marking epsilon 1 here to distinguish from the other expressions we're going to do. And so if I factor out delta x, I get that delta u equals g prime of a plus epsilon 1 times delta x, where epsilon 1 goes to 0 as delta x goes to 0. Similarly, delta y is f prime of b delta u plus epsilon 2 delta u. Again, it's the same thing here, right? Delta y, we're just applying this definition. Remember, u equals g of x, that's why delta u has g in place here. Okay, so when we factor the delta u out here, we get f prime b plus epsilon 2, all times delta u, where epsilon 2 goes to 0 as delta u goes to 0. So now we take delta y, and we're going to replace delta u in the expression for delta y with the full expression for delta u. So we get f prime of b times parentheses g prime of a plus epsilon 1 times delta x plus epsilon 2 times g prime of a plus epsilon 1 times delta x. And this equals the following. So what do we see here? We've got a common factor here of this delta u. We factor that delta u out, g prime of a plus epsilon 1 delta x. We factor that out. And so we get f prime of b plus epsilon 2 times g prime of a plus epsilon 1 all times delta x. So if delta y equals this thing, then delta y over delta x equals f prime of b plus epsilon 2 times g prime of a plus epsilon 1. And when delta x goes to 0, delta u goes to 0, and hence both epsilon 1 and epsilon 2 approach 0. So in other words, the limit as delta x goes to 0 of delta y over delta x is f prime of b times g prime of a, right? Epsilon 2 and epsilon 1 approach 0. But b is g of a here. So we get f prime of g of a times g prime of a. Okay, so that's our proof for the chain rule. It is a little bit of a tricky proof, and all of that trickiness lies around the fact that if we try to think of this as just canceling, we could be dividing by 0, which would cause us some problems. So yeah, that one's a little bit tough, but let's actually tackle some problems. So again, I want to think about this in terms of the Leibniz notation, though. That's going to make these problems a lot easier. So when I see this, I'm thinking dy dx equals I'll write du this time, times du dx. So, and okay, well, this looks like du over du cancels, right? It basically does, even though, you know, technicalities. Okay, so what I'm going to do is say, well, I want dy dx, but I don't actually know how to take this derivative directly in terms of x, because inside the function, the exponential function, I have this other expression. So what if I just replaced it with u? Well, I know how to take the derivative of y with respect to u then. That's easy. The derivative of e to u with respect to u is u. But, okay, what is u? U is 4x. I do know how to take that derivative. And so I've got dy du. How do I get rid of the du? I cancel it with a du up here, sort of, kind of. So du over dx. And so then I go, okay, well, what are these derivatives? Dy du is e to the u. That's really easy. And du dx is 4. And now I'll just write that 4 in front and replace u with 4x, so that everything is written back in terms of x. And there's my derivative, dy dx. Done. Okay, so that sometimes can seem a little tricky at first, so we're just going to do a whole bunch of examples of this, and hopefully it won't feel too tricky after that. Okay, so I've got sine of t cubed plus 1. This is f. I want the derivative of f with respect to t. But I don't know how to take this derivative directly because I have this function inside of sine. So I'm going to replace that function and call it u. And I do know how to take the derivative of f with respect to the variable u. That's nice and easy. But I got to get rid of that du down there, so I'll put up a du up there to cancel it, sort of, kind of. And du, well, what's u? U is t cubed plus 1. Do I know how to take that derivative? Yes, I do. So this will be du dt. All right, well, df du, the derivative of sine of u with respect to u is cosine of u. And the derivative of u with respect to t is just 3t squared plus 0. All right, and now I'll write that 3t squared in front times cosine of, and this is cosine of u, but u is t cubed plus 1. Done. Now, for those of you who look at outside examples or have seen any of this before, you may be thinking, oh, well, I can write a little bit less if I just use prime notation. And what we'll see is that as we start dealing with very complex chain rule problems, the prime notation really falls apart. So we're going to do a few more of these simple single chain examples. And then we'll take a look at repeated. Well, we'll do one more of these single chain examples, and then we'll look at some repeated chains, and then it'll be really, I think, clear why this organization strategy is very important. But again, I'm only going to deal with these with the Leibniz notation anyhow, because I don't think it's worth spending any time on prime notation. Okay, so here I've got tangent of sine inverse of x. The function is g. I want the derivative with respect to x, but I don't know how to take this with respect to x directly, because instead of having tangent of x there, I've got tangent of this function sine inverse. So I make a little substitution, call this tangent of u. And so, oh, well, I know how to take the derivative of tangent of u. So this will be dg du, but I got to sort of kind of cancel the du. So I put a du up here. Well, what's u? U is sine inverse of x. I know how to take that derivative with respect to x. So, all right, let's go dg du. That's tangent of u, take the derivative, secant squared of u, times du dx. Well, that's 1 over the square root of 1 minus x squared. So this is secant squared of sine inverse of x divided by the square root of 1 minus x squared. Now, I do want to say this is correct, and this is essentially done, but whenever you have this composition of trig inverse functions inside of trig functions, it's pretty common to be able to simplify that using some of our trigonometry tricks into a way nicer expression. This is going to be one of those examples. So remember, the output for sine inverse is an angle theta. So we're looking at theta equals sine inverse of x. So that means sine of theta equals x. And we could write this as x over 1. So if this is theta, sine is opposite over hypotenuse. And when I solve for z here, I'm going to skip that step, but I'll get 1 minus the square root of 1 minus x squared. So that means that secant of theta is adjacent, I should say, hypotenuse over adjacent, right? It's 1 over cosine. And so secant squared of theta would be 1 over that square root squared. Okay, so now I can plug this secant squared of theta result back into here. And I get 1 over the square root of 1 minus x squared squared divided by the square root of 1 minus x squared by itself. That's 1 over the square root squared times 1 over the square root, which is 1 over that square root cubed. Okay. So that's, I think, a much simpler expression to deal with than the original expression we had. But generally speaking, I'd probably be fine with seeing this. But if you needed to do more with this expression, you'd really want to simplify it down further. Okay, so let's move on. So now here's when things get a little trickier. So now we're going to start extending the chain rule. So the chain rule extends to additional composite functions in the natural way, as seen below. So here, we're taking the derivative of f of g of h of x. So now we have 3 functions with 2 composed inside the first one. And so that's df dg times dg dh times dh dx. And again, we kind of think of it like these things cancel, even if it's not technically correct. So let's apply the same thought process we were applying before to these types of functions. And these types of functions are going to seem pretty complex at first, but we'll see that they're really quite simple if we're using this approach. So df dx. Well, I can't take this derivative directly because I have this thing inside of my outermost function. So we always look at the outermost function first, that's sine, and inside it I've got this mess of other functions. So I need to replace that, and we'll replace it with u. So I can take df du, but I got to get rid of the u. So let's take a look at u. U is e to the 7x. And now I'm in a similar situation. I don't know how to take the derivative of e to the 7x directly. I know how to do e to the x, but not e to the 7x. So I make another substitution, and we'll replace 7x with v. So v here is 7x. So now I know how to take the derivative of u with respect to v, so I can take du dv, but I need to end up with x on the bottom, so I got to get rid of this dv too. Now I look at v. Do I know how to take its derivative with respect to x? Oh yeah, I do. That's just 7x. I know how to deal with that one. So now we go down the line and we do everything we've been doing. df du. Look at f with respect to u. The derivative sign is cosine. Times du dv. U with respect to v. So I'm taking the derivative of e to the v. That's still e to the v. Times dv dx. The derivative of 7x is just 7. And now, as I'm cleaning this up, I'll move the 7 to the front. And I kind of like the exponential at the front too. So this is e to the v. And v is 7x. So this is e to the 7x times cosine of u. And u is e to the 7x. So remember, we're substituting back to where everything is in terms of x again. Okay, so there we go. That's it. We've got our derivative with respect to x. Okay, so let's go ahead and take a look at another example here. Now here, we have 1 over the cubed root of secant of 3t squared plus 5t plus 1. Again, looks kind of like a mess. But we're going to rewrite this function first a little bit and see that a little bit of algebraic rewriting can also help make these simpler. So instead of the cubed root, we'll write this as the 1/3 power. And then instead of 1 over this, we'll take the negative exponent. So now I look at this and I say, well, what's my outermost function? It's this whole thing to the negative 1/3 power. That's the outermost operation. So I'm going to rewrite this as u to the negative 1/3 power. And u is going to be secant of 3t squared plus 5t plus 1. All right, so let's go ahead and write out our rules so far. We want dg dt. We're starting with dg du. Right, this is the function g. We replaced the inside of the function with u. Now we need to get rid of du on the bottom. So we look at u, and oh man, look at that again. I don't know how to take this derivative directly because I got all this stuff inside the secant. So we'll replace that inside the secant with v. So v is 3t squared plus 5t plus 1. So du dv du dv. And again, I want to get rid of dv. And I look at v and I go, oh, that's a function of t. That's what I'm looking to end up with. I know how to take that derivative. Boom, dv dt. So now we start writing out this product, dg du. I look at the derivative of g written as a function of u. That's negative 1/3 u to the negative 4/3 times du dv. So that's the derivative of the secant of v, which is just secant of v times tangent of v. And now I look at the derivative of v with respect to t, and that's 3t squared plus 5t plus 1, so the derivative is 6t plus 5. And now, as always, we got to go back and resubstitute everything. So I'm going to do a couple little things at once here. First of all, I'm going to put this negative 1 out in front over 3 times, and I'm going to put my u to the negative 4/3 power in the denominator to the 4/3 power. And then I'm going to plug u back in, which is just the secant of 3t squared plus 5t plus 1. And then up top, we've got secant of v, tangent of v. So that's secant of 3t squared plus 5t plus 1 times tangent of 3t squared plus 5t plus 1 times the 6t plus 5. So I just want to reiterate that, you know, every step of this is actually very simple, even though we get what looks like a very complex answer. If you know how to write out this Leibniz rule correctly, then what we're doing is turning one very complex derivative that would be very hard to write otherwise, and we're turning it into a product of 3 derivatives that are simple. Honestly, the hardest part about these problems is that once you've taken your derivatives, you have to plug those variables back in correctly, and so you have to be really careful about that part. But as long as you break it down like this, it's really you're taking one hard problem and just turning it into several really easy problems. Okay, so to finish off this idea, well, I've got a real doozy here. Evaluate the derivative of f of x equals sine inverse of tangent of e to the cosine of ln of x squared. Whew! That should look pretty rough. But again, as long as we just break this down into simple parts, it's really not a problem. So my outermost function is sine inverse, so this is everything inside. So I'll make my little substitution, sine inverse of u. So I want the derivative of f with respect to x, but I'm going to start with df du. Now I got to look at the function u. U equals tangent of e to the cosine of ln of x squared. Okay, so du d what? Well, I don't know how to deal with all this, but if I look at my outermost function tangent, we can just make this tangent of v. Okay, well, I know how to deal with that, so du dv is pretty simple. Okay, now what about v? What's this whole v thing? Well, v is e to the cosine of ln of x squared. Oh no, what do I do? Well, look, it's just e to this thing here. It's e to the w, we'll call it. Okay, so now I need to get rid of dv, so I need dvd. Oh, my new variable is w. Well, what's w? Well, it's just cosine of ln of x squared. Okay. Well, now what? I replace this. How about we'll call this cosine of z. Oh, okay. Well, that means I can get rid of dw by taking dw dz. But what's z? Oh, it's ln of x squared. Now, you might think you need to do another composition here, but if you realize, oh, this is just a log rule, I can do this as 2 times ln of x, you can save yourself some trouble. Okay, so then I look at z and I go, oh, now I know how to take this derivative with respect to x. So this is dz dx. So altogether, it seems like a really rough problem, but each of these individual derivatives is really easy, right? df du, the derivative of sine inverse of u, that's 1 over the square root of 1 minus u squared, times du dv. Okay, du dv, the derivative of tangent of v is secant squared of v. Okay, dv dw. The derivative of v with respect to w is e to the w. dw dz, I look at w. Derivative cosine is negative sine of z. And dz dx, well, that's 2 times 1 over x, or 2 over x. And so now it just comes back to the same old plug in all the numbers routine. So I'm going to put the negative and the 2 out in front because we can multiply in any order. So negative 2 And then we've got secant squared of v, and v is this whole thing, e to the cosine of ln of x squared. Times e to the w, and w is cosine of ln of x squared. Times sine of z, remember I already put the negative out in front, so this is sine of ln of x squared. And remember I already put the 2 in front, so on the bottom, I'll move this x to the front, times the square root of 1 minus u squared, and that's really the biggest problem, is just fitting all of u into this expression. Tangent squared of e to the cosine of ln of x squared. Woo! We did it. Okay, that's the whole thing. And that's, I mean, that is like the worst case scenario for a chain rule derivative. It cannot get any worse than that. But hopefully you see that even though there's a lot of things being written here, what we're doing is just taking what seems like a really complex function to deal with and just turning it into a product of 5 really easy derivatives. And then again, the hard part really is just going to be carefully plugging back in your variables, trying to make sure you don't make a mistake there. Okay, so that's it for those examples. Let's go ahead and move on to something a little different. So here we've got a chain rule, but inside the function is a product. So things end up going a little differently here. So I start with my usual log base 2 of e to the x times cotangent of x. Sorry, I should say I rewrite that with u here. So I want dy du. I want dy dx. And I'm starting with dy du. Okay, so we have to deal with what is u here, and do we know how to take its derivatives in a useful way? Okay, so u is e to the x times cotangent of x. And when I look here, I don't need another chain rule. I just need the product rule. So this is really du dx. I can just stop there. So now when I write this out, dy du, right, the derivative of log base 2 of u is 1 over x times log base 2 of e, multiplied by du dx. But when I take du dx, I need a product rule. E to the x prime times cotangent of x plus e to the x times cotangent of x prime. And if you wanted to do this product rule off to the side and then plug the result back into here, that would be totally fine. Yeah, there'd be no problem with that. But here we get log base 2 of e over x times e to the x, the derivative of e to the x is e to the x, times cotangent of x plus e to the x times the derivative of cotangent is negative cosecant squared. The only thing I could really do here is factor the e to the x out, which I'll go ahead and do. So this is e to the x times log base 2 of e over x times cotangent of x minus cosecant squared of x. Okay, so that's it for that example. Let's move on. Okay, so here we have a similar idea. We've got inside our function is a quotient. So when we rewrite this as u cubed, we see that u is z squared over z cubed plus 4. So I want the derivative of g with respect to z here. So that's dg du times du dz. So when I go to apply this, well, dg du, that's easy. That's 3u squared. just reminded me, did I plug my... Oops, I made a very silly mistake earlier. That should have been 1 over u times ln times log base 2 of e. Sorry about that, everyone. That was the derivative with respect to u here. And so I got to plug that u back in. It's e to the x times cotangent of x. I don't know why that just popped into my head that I'd done that, but I'm glad it did. So with that e to the x over e to the x, I can actually cancel that. That gives me a nicer expression here. Log base 2 of e times cotangent of x minus cosecant squared of x divided by cotangent of x. Okay. Sorry about that. Let's go ahead and move on. All right, where were we? So we get 3u squared times du dz. So same old quotient rule. Low d high minus high d low over the low squared. Okay, I plug u back in, so I get 3 times z squared over z cubed plus 4 squared times 2z, so I'll get z cubed plus 4 times 2z minus c squared, and the derivative of this will be 3z squared. Now, I will point out that there is some simplification that can be done here. You get z squared squared is z to the 4th. You can multiply that across here. You can multiply this stuff out. And in the bottom, you'll end up with z cubed plus 4 to the 4th power. And that will make things a little bit cleaner and easier to work with. For the sake of time in this video, I'm going to leave that as an exercise to the reader on the simplification there, and just move on to the next problem. So, given that h of x equals f of g of x, use the image below to compute h prime of 4.5 and h prime of 0.5. So this is one of those very rare cases where using prime notation for the chain rule is actually helpful, sadly. So in this case, because we've got to keep track of the individual points when we're doing this, it actually is a little easier if we think, okay, h prime of x here is f prime of g of x times g prime of x. So h prime of 4.5 is the derivative evaluated at g of 4.5 times g prime at 4.5. So let's go ahead and take a look. What does that give us here? So when I look at f prime, well, first I need to know what is g of 4.5. Well, when I go look at g and I go to 4.5, that's 1/2, 1, and this is another quarter. So that's 5/4. So g of 4.5 is 5/4. And g prime of 4.5 is the slope here. And I'm going up 3, 1, 2, 3, and over 1. Or over 2, I should say. So that's 3 over 2. So now I'm looking at f prime of 5/4. So when I go to 5/4, that's 1 1/4. What's the derivative of f here? Well, the slope here is rise 2 and go over 1. So that's 2 over 1 times 3/2, which is 3. Okay, and now when we look at h prime of 0.5, so again, the way we'd have to write that is f prime of g of 0.5 times g prime of 0.5. So what's g of 0.5? Oh, that's 1. So this is really f prime of 1 times, and what's the slope at 0.5 for the function? Oh, I was looking at the wrong function there. I better make sure I was looking at the right function before. G of 4.5. Yeah, that should be 5/4. Yeah. G prime of 4. Yeah, okay. I was looking at the right thing there. F prime of 5/4. Yeah, I was looking at the right thing. Okay. That should not be 1. G of 0.5. G is the black graph. That's 2. So that should be F prime of 2 times G prime of 0.5. So we go up to G, and in this case, this derivative is 0 because the slope here is 0. I don't even need to do anything else. The result is 0. So that derivative is 0. All right, that's it for that one. So I'll just pause here for a moment in case you want to look at that a little bit more. All right, well, let's go ahead and move on now to this final example. Evaluate the derivative of f of x equal to the natural log of the absolute value of x. So the first thing is to recognize that this has to be defined piecewise. So this will be the natural log of x for positive values of x, and it will be the natural log of negative x for negative values of x. And we don't have to worry about x equal to 0 because the natural log is undefined at 0. So we're going to look at what's the derivative for values greater than 0. So we get the derivative of ln of x, which is just 1 over x. That's nice and simple. When we look at negative values, we're looking at the derivative of ln. So let's go ahead and write this out. So we're going to have a chain rule here. Y equals ln of negative x. So I'm going to think of this as ln of u. And this is dy dx equals dy du times du dx. So dy du is 1 over u, and du dx, well, u is negative x. So I get negative 1 for that derivative. So this is negative 1 over negative x, which is 1 over x. So I happen to get the same derivative for both the natural log of x and the natural log of negative x. So what that tells me is that in general, I can say that the absolute value of the natural log of the absolute value of x has the derivative just 1 over x. Okay, well, that's it for that example. Thank you for watching.